Have you ever wondered how chemists can figure out the exact amount of a metal just kind of hiding out in a solution? I mean, it sounds super complex, right? But the answer is this really elegant and honestly kind of beautiful, colorful process. Today, we are unlocking the secrets of complexometric titration. It's basically chemistry's very own color-changing magic trick.
Seriously, think about that for a second. How do you measure something you literally can't see? Whether it's testing the hardness of your drinking water or making sure a medicine is pure, we need a reliable way to count those invisible metal ions. And that is the exact problem complexometric titration was born to solve. Okay, so here's our game plan. We're going to start with the basics. What even is this thing? Then we'll meet the cast of chemical characters that make it all happen. After that, it's the main event, the titration process itself. We'll also look at a few different tools in the chemist's toolkit. And finally, we'll wrap it all up by seeing why this clever trick actually matters in the real world.
So, let's dive right in. What exactly are we talking about when we say complexometric titration?
Okay, so at its heart, it's a way to measure stuff. We're figuring out the concentration of metal ions by very carefully adding another chemical. And we keep adding it until we see a super specific color change. That color change is our signal. It tells us we formed a special kind of molecule called a complex.
You know, to really get what makes this special, it helps to compare it to another method, precipitation titration. In that one, your signal is, well, a solid chunk suddenly appears in your liquid. Kind of clunky. But complexometric titration is so much more elegant. Instead of a solid, we're watching for a sharp, clean color change within the solution itself. It's really the difference between making mud and perfectly dyeing water.
All right, to get how this all works, we've got to meet the players. So let's think of this less like a boring lab procedure and more like a tiny molecular drama playing out right there in a beaker.
First up, our target, the metal ion. This is the whole reason we're here. It's what we're trying to measure. Now, chemically speaking, it's a Lewis acid, which is just a fancy way of saying it's on the lookout to accept a pair of electrons. Basically, it's the prize that everyone's after. So who's trying to grab this prize? Meet the ligand. This is our complexing agent. It's a Lewis base, which means it's ready to donate its electron pairs. And get this, the word chelate actually comes from the Greek word for claw, and that is the perfect description. This molecule is literally designed to reach out and grab onto that metal ion and just not let go. Now, there are a lot of ligands out there, but the undisputed superstar of the show is EDTA. So what's its secret? It's something called hexadentate. That means it has 6, count 'em, 6 points of contact. Think of it like a claw with 6 fingers that can all wrap around a single metal ion at the exact same time. This crazy grip creates an incredibly stable bond. It's like a chemical lockdown. And that stability? That's the secret sauce for getting a super precise and reliable measurement every single time.
Okay, let's put our players into action. The whole process really boils down to a competition. It's a tale of 2 different claws fighting over the very same prize, that metal ion.
So here's the play-by-play. First, we add a special indicator dye to our sample. This indicator is our weak claw. It grabs onto the metal ions, and when it does, the whole solution turns this really distinct wine red color. Okay, step 2. We start slowly dripping in our strong claw, the EDTA. Because EDTA is just so much better at grabbing the metal, it starts systematically stealing the metal ions away from that weaker indicator. One by one, the ions are snatched away. Now here's the crucial part. We keep adding EDTA until the very last metal ion is gone. The moment that last ion gets snatched, the indicator is suddenly left all alone. And when it's free, it instantly changes to its true color, a brilliant, beautiful blue. And that right there is the magic moment. That sudden, sharp flip from wine red to blue is our signal. It's the endpoint. It tells us, with incredible accuracy, the exact moment every single metal ion has been captured. And since we know exactly how concentrated our EDTA is, we can just look at how much we added to calculate the original amount of metal. It's really just elegant visual math. Now, that direct approach we just talked about is fantastic, but, what happens when things get a little tricky? Well, chemists have developed a few other clever variations to handle all sorts of situations. It gives them a whole flexible toolkit. What we've been describing is called direct titration. It's simple, it's fast, it's usually the first choice. But what if your metal reacts super slowly, or you just don't have a good indicator for it? That's where back titration comes in. It's this really clever workaround. You add a known excess of EDTA, like way more than you need.
The EDTA grabs all your metal, and then you do a second titration to figure out how much EDTA is left over. You just subtract what's left from what you started with, and boom, you know how much you used. And finally, you've got replacement titration. This is for the really tough cases. Here, you let your target metal literally kick out another metal from a complex that's already there. Then, you just measure the metal that got kicked out, which often gives you a much sharper color change. It's a bit indirect, but it's a super effective strategy.
Okay, so this is all really cool chemistry for sure, but where does this stuff actually show up in our day-to-day lives? Well, the applications are way more common than you might think.
Probably one of the most common uses is testing for water hardness, which is really just a measure of calcium and magnesium ions in your tap water. In the world of pharmaceuticals, it's absolutely vital for quality control, making sure a drug has the exact right amount of active ingredient. It's also used all the time in industry to check the precise recipe of metal alloys. So yeah, from your drinking water to life-saving medicines, this is a truly fundamental tool for making sure we know exactly what's in stuff.
So there you have it. A simple change in color lets us see the invisible and measure it with incredible precision. It's such a powerful idea. And that kind of leaves us with one final thought. Now that you know the principle, what other invisible things out there could you imagine measuring, just by using a clever color-changing reaction? Food for thought.